Most of the time in survival horror games, the standard enemies you're up against are kinda dumb. Punishing? Yeah. Aggressive? Yeah. But usually they'll forget about you if you leave the room and wait for a bit. This is probably for the best. It would be really annoying if you narrowly made it out of a room, went to do something else, came back inside to pick up more bullets or something, and were immediately jumped by 5 zombies. That being said, there is one type of enemy known for breaking with this convention.
Jesus Christ!
Unlike your standard enemy, pursuer enemies are a constant threat. You always have to be on guard. You don't know when exactly they'll show up, and you want to make sure that they don't know where you are. Fighting them usually isn't an option, since they're designed to be bullet sponges, if they take any damage at all. Really, the best course of action is to just stay out of sight until they're gone. Because they're so integral to moment-to-moment gameplay, having a good pursuer can make or break your game. This is especially true if the pursuer enemy is the only enemy in your game. I can think of at least 2 games off the top of my head where a lot of their criticism centered on the pursuer AI not being as good as people thought it would be. I'm not going to name names, but you can probably guess which games they are. Speaking of which, what makes a good pursuer? At its core, pursuers have to balance 2 competing traits. They have to be good enough to be a constant threat, which contributes to the hostile atmosphere of the game, and makes players feel smart when they avoid the pursuer. At the same time, they have to feel fair. Players need to feel like the pursuer is making reasonable decisions based on the information it has. If the player trips an alarm and the pursuer bursts out the door and starts running at them, well, that's kind of on them. If the player is quietly solving the puzzle and the same thing happens, they'll probably be a bit more upset. This is all easier said than done. The less information the AI has to work with, the less of a threat it is. I think this is why there's been a lot of praise for intelligent pursuers, like the alien in Alien Isolation. You're always in danger, but the pursuer never gets your exact location through divine revelation, so it doesn't feel unfair. In this video, we'll try to put together a pursuer AI that's capable of finding the player based solely on environmental cues. Let's start by examining how humans tackle this problem with the game hide and seek. The seeker starts by starting off knowing exactly where the hider is. Then they close their eyes and count down for like 60 seconds. Because they can't see what's around them, as they count down, they become less and less certain of where the hider is. Once the countdown finishes, they need to figure out where the hider is hiding. By taking a quick look around, the seeker can immediately rule out most of the surrounding area. That leaves places that require more effort to investigate, like behind buildings, underneath cars, or inside bushes. Investigating each of these locations is going to take a lot of time, so the seeker might want to use clues in the environment to focus their search. For example, it could see a footprint in the mud or a rock that was kicked, indicating that the hider was recently in the area. While the seeker is busy, the hider can continue moving around, so it's possible for the hider to end up in an area that was previously searched. This is the basic idea behind Bayes filters. Bayes filters are used to estimate some piece of information you don't have, your hidden state, based on the information you do have, your observations. On each time step, we're going to try to predict how the hidden state could have changed, then use our current observations to narrow down what the hidden state could actually be. For example, let's say you have a robot that's trying to figure out where it is inside of a maze. The robot has multiple sensors that can detect how far it is to a wall. The hidden state we're trying to estimate is the robot's position, based on our observations, which consist of sensor readings. More specifically, we'll split the maze up into a grid and try to figure out which tile the robot's on. We'll start by saying that every part of the maze is just as likely to contain the robot, forming our prior probabilities, our prior. Even though the update step follows the predict step, we'll introduce the update step first, since we're starting with a uniform prior here. In this step, we'll use our sensors to restrict where the robot could be. We need to ask, what's the probability that the robot is in each part of the maze considering our latest reading? In a perfect world, this likelihood map would be unambiguous. There would only be a handful of places that give us these exact sensor readings. We don't live in that world. In our example, if our wall sensor tells us that we're 10 centimeters away from a wall, there's a 90% chance that we actually are 10 centimeters away from a wall, and a 10% chance that we're plus or minus 2 centimeters. These likelihoods are multiplied by our prior to get the joint location probabilities. At this point, the values in the grid might not add up to 1, so we have to renormalize by dividing the grid by the sum of all values in the grid. We've narrowed down where a robot is, but we haven't accounted for its movement. That's where the predict step comes in. Let's say on the previous time step, we told the robot to go right by 1 cell. In a perfect world, we just shift our probabilities to the right, but again, we don't live in that world. The robot could have moved slightly up or down, or undershot or overshot horizontally. Instead of a straightforward right shift, we have to sort of smear it to the right. To do this efficiently, we can use a 2D convolution, which we usually use for image effects like blurring, edge detection, and sharpening. We'll define a 2D matrix, a kernel, that will determine the new value of each cell based on its neighbors. For a rightward shift, the highest weight gets assigned to the mid-left cell, some weight gets assigned above and below, and the rest of the cells get assigned accordingly. After one iteration, even though we've lost some accuracy due to the prediction step, our update step has massively narrowed down where the robot could be. If we repeat this process over and over again, we'll eventually get a pretty good idea of where the robot actually is. I've been calling this a Bayes filter, but more specifically, it's a discrete Bayes filter, since we represent probabilities and likelihoods with grids. If we replace grids with normal distributions, it'd be a Kalman filter, and if we replace them with particles, it'd be a particle filter. We'll be sticking with the discrete Bayes filter because they can represent multiple zones of high probability, and they're easy to work with. Let's bring this back to our hide and seek problem. We're going to basically perform localization, but in reverse. Instead of estimating an agent's own position based on its sensors, we'll instead use the sensors of another agent, the pursuer, to locate the player. Here's our problem setup. We have an 8x8 grid world where cells have a 10% chance of being a wall. We have a player and a pursuer agent that can freely move around, and the pursuer has a vision cone that can't go through walls. Let's start designing this filter. Since we don't know where the player will try to move, we'll say that it's equally likely for the player to move into each of its neighboring cells after each time step. That covers the prediction step. The update step is more complicated. We'll start off by saying that it's impossible for the player to ever be in a cell with a wall. The most important sensor the pursuer has is vision. If the player is inside the vision cone, we know for sure where it is, so the cell it's in gets a probability of 100%, while the rest of the cells get a probability of 0%. If the player isn't inside the cone, the area inside the vision cone gets a probability of 0%, while all other cells are equally probable. You might have noticed that the edges of the cone look anti-aliased. We actually have to do this because you can accidentally rule out a cell that the player is on if the vision cone even slightly intersects with it. Now's a good time to mention that if your filter is too aggressive, it'll break because the entire grid can get set to a probability of 0%. This is bad. Another piece of information usually used by enemies is sound. Let's say the player can emit noise by interacting with its environment, like by moving crates, unlocking doors, or even just running around. We'll give each noise source a radius, where if the pursuer is in range, it'll pick up on it. We could do something similar to the vision cone, where once the pursuer hears a noise source, it'll know exactly where the player is. But that's unrealistic and also boring. Instead, we'll normally distribute the likelihood centering on the noise source, with the spread, or variance, based on how far away the pursuer is from it. If it's really far away, it'll know the general area the player is in. Maybe that the player's somewhere in the next room? If it's really close by, on the other hand, they'll know exactly where they are. Okay, final piece of information. Whether or not objects have been moved. Now this is kind of an unusual one, but I think it works well for this type of game. For each object in the environment, the pursuer will keep track of the last time it saw it and its position. If it's in a different spot the next time it sees it, it can use the elapsed time between the last time it was seen and now to rule out where the player could currently be. This is interesting because with vision and audio, you just have to stay out of the pursuer's sensor range to not get detected. Now the pursuer has object permanence. You have to make sure you aren't leaving any trace of yourself when you're moving around, otherwise you risk the pursuer narrowing down your location later down the line. We figured out how to narrow down where the player is, but now we have to get the pursuer to actually go after the player. While working on this video, I found this article that uses a really similar approach to Bayes filters, but for stealth games. Link in the description. Their approach is based on Markov chains, but the concept is identical. Blur the location probabilities, then use sensors to rule out possibilities. They handle searching for the player by using pathfinding to move towards the cell with the highest location probability. The nice thing about this approach is that by having the agent move towards a location, it'll turn its head towards it, ruling out an entire area at once. They have a demo along with the post, and this does seem to work really well. But how does it work with our setup? Pretty good. That being said, it doesn't hurt to experiment, so we're going to try a deep reinforcement learning approach. Reinforcement learning is a big subject, and the specific technique I'll use here, policy gradients, can look a little scary at first glance. Fortunately, there's a lot of places where you can read up on this stuff if you're interested. There's also libraries that'll just implement it for you. I'll put a link to Godot and Unity RL packages in the description. For this video, I'll just go over the basics. Reinforcement learning, or RL, works on problems where you get some input, choose an action based on that input, and get a reward. By trying different actions over and over again, the algorithm will learn to choose actions that lead to high returns. Returns in this context are just all the rewards you get after a time step to the end of the episode. As input, we'll give the pursuer the output of the filter, plus some things like the pursuer's current position and direction. We'll give the pursuer a reward of 1 when it spots the player, and a 0 on all other time steps. To train the neural network, we'll use gradient descent to maximize the probability of each action times the return we ended up with. If the pursuer didn't manage to find the player in one episode, all the actions it took during that episode would become slightly less probable in future runs. If it did find the player, all the actions would become more likely. Positively reinforce actions that lead to good stuff, negatively reinforce actions that lead to bad stuff. This might sound a little too simplistic, and it is. This specific algorithm is known not to work super well. I'm actually going to use an upgraded version called Proximal Policy Optimization, or PPO, which has a couple small changes that improve the efficiency and stability of the algorithm. There's a link in the description on how that works if you're interested, but again, a lot of frameworks will implement this for you. There's a small hiccup here though, which is that we actually have 2 agents in this scenario, the pursuer and the player. Up until now, we've been using an exploratory policy to control both agents. It pretty much just moves randomly, doesn't move into walls, and tries to avoid the other agent if it can. If we had the player controlled by this policy while we optimize the pursuer, we would learn to be really good at locating this specific player, but not a player that acts realistically. For example, an agent using this policy doesn't hide behind walls like a normal person would. For that reason, we'll be training both the pursuer and the player at the same time. Fortunately, PPO has been shown to work in both the single agent and multi-agent scenario, although there are a couple changes you have to make for the best results. Some of these are just saying the hyperparameters a certain way, like using a low epsilon and not using mini batches. Changes that make training slower, but more stable. A bigger change is giving part of the algorithm access to all agents' observations, which guides training towards better actions across all agents. This is called centralizing the critic. If you want to try this for yourself and you're using the framework, choose the MAPO algorithm to get all this stuff for free. Let's see how our algorithm did. I'm showing the entropy over time on the side here of both agents. Entropy just means the randomness of the actions, so a completely random agent would have high entropy, while an agent that always does a certain action for a given input would have low entropy. As you expect, as time goes on, the entropy generally goes down since the agents become more sure of the actions they want to take. I'm also going to show the pursuer's performance against a player controlled by our exploratory policy, since the performance of the player it trains against changes over time. You can actually see that it looks like it gets worse over time when playing against our trained player, while it gets better over time against the exploratory player. Initially, both the pursuer and the player act pretty randomly. At around the 2000 mark, we see the player is pretty consistently moving away from the pursuer, while the pursuer is focusing its search around the area that the player should be in. With further training, the pursuer gets laser focused on trying to find the player. As we'd expect from the reward curve, the player is really consistently avoiding the player and deploying common avoidance strategies, like when it kites around a block to keep itself out of sight. So great, it works. But the million-dollar question is, does this work better than pathfinding? Well, no. I compared the baseline, pathfinding, and learned policies, and even though the learned policy did do better than the baseline, it still did worse than using pathfinding.
This isn't the full story though.
Remember, our baseline player isn't the smartest, it just kinda wanders around. I also benchmarked our pursuer policies against our learned player, and found that the learned policy is actually on par with pathfinding in this case. Granted, they all perform pretty terribly and fail to find the player over 95% of the time. With all said and done, here's my thoughts on the matter. If you want to equip a pursuer with a Bayes filter, start off by using pathfinding. As we've seen, you'll get really strong results right off the bat, and even if your engine doesn't support pathfinding out of the box, it shouldn't take more than a couple hours to get a working A-star implementation. As your game gets more complicated, you might find that pathfinding isn't cutting it. Maybe your pursuer needs to be able to unlock doors, destroy parts of its environment, or set traps. Even though RL can take a lot of effort to get it working at all, once you do, the work needed to adapt it to harder problems can be way less than using more traditional techniques. Now, we didn't actually do any experiments to show that RL will definitively do better in these scenarios, but the video is already getting kinda long, so I'm gonna play further research needed here.
Okay, let's recap.
We demonstrated how discrete Bayes filters can be used to estimate the player's position. We showed off a couple common types of observations and how you can implement them. Then we used multi-agent reinforcement learning to train the pursuer to chase the player. We found that RL does work in this scenario, but doesn't necessarily do better than pathfinding, which works more consistently and doesn't require like 2 days of training. And that's pretty much it. I have code and an online demo linked in the description, plus links to the stuff I talked about in the video. If you got the time, I encourage you to check them out.